How this looks like. Here, for instance, I show you an SE image of an austenitic sample. We have the typical contaminations which we can see in SE mode and a few dust particles which can be applied for the focusing. And you know that if we go now to a four-scattered signal, the conventional one shows you grayscaled images. You see immediately how nicely you see all these details. But if of course, you know it from the black white and the color TV. Color TV is more important, much better. It gives you more information for colors which produce the same grayscale. And this you can simply do by this detector. If we switch to our colored mode, you see then that many images, for instance, please take this grain here into account. And if I go back, for instance, to the grayscale image, you see there are no grain boundaries or twin boundaries anymore. The same happens, for instance, and this grain here. You see it here. We have again twins, which we can't see because simply they're grayscale. If you transfer this color into grayscale, they are similar. This helps you much better to find a region of interest, of course, if you want to define your map, and that's a very helpful feature in your preparation of your measurement. As a few simple examples, here on iron meteorite, the microstructure is called white plessite. It's a small grain sized material and shows a ferritic matrix. And we have there a few lines which probably describing grain boundaries, but in print we are not really sure because we have many changing of these contrasts which are coming from the channeling, the local channeling. And if we cover this in color, if you color this, you see immediately and very nicely that, for instance, for several lines you probably misinterpreted them, but in the colored mode you see that's much clearer that you see that you have different orientations. The ferrite in martensitic steel, we have here residual ferrite, and these were ones at high temperature austenitic grains, and they have been transformed into martensite. On the sample surface topography, you already see, okay, there are definitely different so-called variants, which show grains of different orientation. And if you go to the color mode, it looks like that you see much better how orientations can be visualized. There's no quantification possible, at least at the moment, but it shows very nicely different orientation. You can select a region which are probably interesting for an EBSD map. If you want to combine it with a BSE detector, there's a multi-phase steel showing bright carbides, tungsten carbides, and also a few titanium carbides which show not that big contrast because they have less intensity. And if you combine it with the four scattered dyes, that means with orientation, determination, you see in the background now the matrix orientations. We have small grain areas and large grain areas which you can't see before. That means if you're really interested in small grain areas like here, you can then specify or define this area simply for a better interpretation of your material. Tantalum, nicely shown here, this shear bands within grains. It's amazing what you can see with this detector. It also works for rocks as well. Of course, the major, let's say, influence is that the material is crystalline, because as I mentioned, as I showed the sketch of this detector, we cover parts of our backscattered electron, EBSD pattern. That means we can only see here these contrasts if we have a backscattered electron signal. That we have an EBSD pattern, so that we can say this can be also used as proof that the preparation is quite, let's say, suitable for an EBSD interpretation. It means it's also useful for this application. If this is, by the way, it's overlaid by the element of density contrast. Here we see a slightly brighter silicate. That's a little bit less dense silicate here. And if we remove this, there's now the orientation contrast, because the